A very warm welcome to all the budding scientists. Now, moving on to second part of electricity, starting from Ohm's law. Ohm's law states the relation between the resistance, the current and the voltage flowing across the circuit. It describes how the current and the voltage change with each other. They are related to each other. What is the relation between them? The statement of Ohm's law states that the current flowing through a circuit is directly proportional to the voltage applied across it, provided the temperature remains constant. Temperature is a property that should remain constant throughout the experiment. Only then we can observe the relation between current and voltage flowing across the circuit. It establishes a relation between current and potential difference. Let's suppose the symbol for current is I, symbol for voltage is V. Then, according to Ohm's law, if we state it mathematically, it states that I, that is current, is proportional to V voltage. Bracket, at constant temperature. This is important. If the temperature changes, the experimental readings will be disrupted. So we can also say if I is proportional to V, then voltage is also proportional to I. Now, if we want to remove the sign of proportionality and introduce a sign of equality, then we'll have to put a constant of proportionality. Here, the constant of proportionality will be R. So, V equals R into I. This R is the constant which is known as resistance, or you can also say this is the resistance constant of the circuit. The resistance of a circuit is measured in ohm, represented by a Greek symbol omega, and this is the SI unit for measuring the resistance. Now, just as we defined 1 ampere, 1 volt, similarly you will also ask to define what is 1 ohm. 1 ohm is the resistance when 1 ampere current flows through a circuit whose voltage is 1 volt. 1 ohm resistance, 1 ampere current and 1 volt voltage. This is how you can define the unit of resistance. This graph shows the relation between the current and voltage flowing through a circuit. If voltage is 0, current is also 0. So the graph starts from the origin. In this graph, you can see that current and potential difference or voltage are related in a linear relationship. That means they change with each other linearly. Direct relationship because the graph is moving from origin in the positive direction upwards. The straight line says that the ratio of voltage and current at any point of time will bear a constant ratio with each other, provided the temperature is constant. If the temperature changes, then this line will not be a straight line, this will be a curved line. It clearly demonstrates the potential difference increases, the current also increases. This constant, as we did in the previous slide, is also known as the resistance of the conductor or resistance constant. Now, we have understood what resistance is. Now we'll define it and we'll try to calculate it. Suppose we are moving in our vehicle and the street is not a broad one, a narrow one, and there are about 50 vehicles already moving through that street. So we'll face some resistance in our motion. We'll not be able to move our vehicle at a higher speed. It will move slowly. You say that traffic is more, my vehicle is suffering resistance and it is not moving at a high speed. But the same scenario, same number of vehicles, and in place of street we have a highway, a 6-lane highway. Then you will not face any resistance. You will move your vehicle at a very high speed. Similarly, the resistance is the property of the conductor through which it opposes or obstructs the flow of current through it. When the current is flowing through a circuit, through a conductor, the conductor offers some resistance, some opposition towards the flow of current. This is known as the resistance of the conductor. And the resistance of a conductor is equal to the potential difference between its two ends divided by current. That means we say that resistance of a conductor is equal to the voltage across it divided by the current flowing through it, where V is the voltage or potential difference, I is the current, and R is the resistance. And previously said, the SI unit of resistance is ohm, represented by a omega. In this picture, you can see the resistance. Diagrammatic representation of a resistance is a zigzag line, and actually in the circuits when we connect resistors, the resistors are of different types and look like these. Now there are some factors affecting resistance. Some external factors which increase or decrease the resistance. The first factor is the length of the conductor. The conductor is long, resistance will be something else, and if the conductor is short, the resistance will change. Accordingly, the area of cross section. Always remember that a wire, a conductor, is considered to be cylindrical shaped, and if it is cut, the cut end represents a circle, and the area of that circle is the area of cross section of that conductor. So if the area of cross section is increased, it affects the resistance, and if the area is decreased, it affects the resistance in an opposite manner. Like we say, a thick wire has some resistance and a thin wire will have a different resistance, even if they are made of a same material. Third, the nature of material. The material which we are using for our conductor also affects the resistance. Let's suppose if we are using a good conductor, it will offer less resistance, and if we are using a poor conductor, it will offer more resistance. And finally, the temperature. The increase and decrease in temperature also affect the resistance. How is it? We'll discuss now. Effect of length. If the length is increased, the resistance will also increase. That means resistance is directly proportional to the length of the conductor. A longer conductor will have more resistance and a shorter conductor will have less resistance. Number 2, area of cross section. If the area of cross section is increased, the wire becomes thick, and a thick wire offers less resistance because there is more surface area for the charged particles to travel without any hindrance. And if the area of cross section is decreased, the wire becomes thin and the resistance of the conductor increases because the charged particles now have less area for their movement. So we can say that a thin wire has more resistance and a thick wire has high resistance. So resistance is inversely proportional to the area of cross section of a wire. Third, nature of material. If we are using good conductors like gold, silver, copper, then the resistance of the conductor will be less. But if we are using materials like iron or lead, then the resistance will be more because these materials are not as good conductors as gold and silver. Finally, effect of temperature. The same conductor will have less resistance at a lower temperature, but it will have a high resistance at a higher temperature. So we can say that as the temperature increases, the resistance of the conductor also increases. Reason being, when the material is heated, the atoms are agitated. They have high kinetic energy and they collide with the moving charged particles. Therefore, the moving charge particles will suffer more resistance due to increased number of collisions. So, at higher temperature, the resistance is high. Resistivity. This is a concept related to the resistance of a conductor. Resistivity is also known as specific resistance. So, if you are in your textbooks, if specific resistance or resistivity, whatever is written, they mean one and the same thing. We have learnt that resistance is directly proportional to length and resistance is inversely proportional to area of cross section. From equation 1 tells us the relation between the resistance and length, and the equation 2 tells us the relation between resistance and area of cross section. If we combine both these equations, this becomes R proportional to L upon A. Now, to remove this proportionality sign with an equality sign, we have to insert a constant of proportionality, that is rho. This looks like a small p, but it is actually a Greek letter rho. This represents a constant known as resistivity or specific resistance. Specific resistance is always constant for a given material. Suppose we are using copper. So copper wire will have the resistivity same whether the wire is thin, whether the wire is thick, it is longer or shorter. It will have no effect on the resistivity of the material. Resistivity represents how strongly a conductor is opposing the flow of current. In good conductors, the resistivity is very low, and in bad conductors or poor conductors, the resistivity becomes high. And if the resistivity is very, very high, then that material is known as insulator. It will not allow any current to pass through it. Now, let's read about the combination of resistors. What is a resistor? Any conductor which offers some resistance is known as a resistor. Now, these resistors may have different values. If the resistors are combined in series, like this one, R1 connected to R2 connected to R3, and this serial combination is connected in a circuit with a battery. Now, in this case, the current leaves the positive terminal, enters resistor 1, then resistor 2, then resistor 3, and finally goes back to the battery. In this case, the potential difference or the voltage of the battery is distributed among these three resistors. So, first resistor will have potential difference 1, V1, second will have V2, and third will have V3. Now, by convention, we have the total voltage of the battery is distributed among the three resistors not equally, but in the ratio of their resistances. V1 plus V2 plus V3 will be equal to V. So, in the series combination, the current flowing through each resistor is same, but each resistor is having different values for their voltage. They will be sharing the total voltage supplied by the battery among themselves, in the ratio of their resistances. If R1 is more and R2, R3 are less, then R1 will share a greater portion of potential difference as compared to R2 and R3. Now these resistors can also be connected in a parallel combination. R1 parallel to R2 parallel to R3. In this case, again the current leaves the battery, reaches the junction, and at this junction, at this joint, the current gets divided in the three arms of the combination. Some current goes to R1, some to R2, and the remaining to R3. And at the junction B, all these currents, these three currents will unite and follow the circuit. Here, the voltage of the battery will not be distributed among these three. These three will have the same voltage as supplied by the battery. But what is distributed? The current. The total current leaving the battery gets distributed among these three resistors, again in the ratio of resistances. But here, if R1 is high, it will have less current in it, and the low resistances will have more current in them. And finally, the current reunites at this junction. So, in the series combination, current is same and voltage is getting divided, but in the parallel combination, the voltage is same and the current is getting divided. This is the explanation of series and parallel combination. Now, how to calculate the equivalent resistance of a series combination or a parallel combination. In a series combination, the total resistance, the effective resistance or the equivalent resistance is given by the algebraic sum of all the resistances taken in order. Whatever be the value of R1, R2 and R3, they get added and together they will constitute the equivalent value of the series combination. So, the total resistance in a series combination is the sum total of all the resistances. But that's not the case in the parallel combination. In the parallel combination, the effective resistance is not calculated as in a series combination. In this, we can say that the reciprocal of the effective resistance, the reciprocal of effective resistances is the sum of reciprocals of the individual resistances taken in order, like 1 by R, the reciprocal of effective resistance is equal to reciprocal of resistance 1 plus reciprocal of resistance 2 plus reciprocal of resistance 3. So 1 by R equals 1 by R1 plus 1 by R2 plus 1 by R3 and so on. No matter how many resistances are there, these will be taken in this manner only. Also, you may mark one point: if there are n number of resistances which are of equal value R, let's suppose there are n resistances each having a resistance R and they are combined in a parallel combination, then the total resistance is given by individual resistance divided by number of resistances. You may note this down: when n equivalent resistances are connected in parallel, then the total resistance, effective resistance R is equal to individual resistance divided by total number of resistances. The heating effect of current is a process in which electrical energy is transformed into heat energy as the current passes through any conductor. When a conductor has some current passing through it, it heats up. That's why when we are passing the current through a wire for a longer time, there is slight increase in its temperature. that is due to the heating effect of electric current. This amount of heat generated is dependent on two things. First, the current that is flowing through it, and the number two is the resistance of the wire. If same current is passing through two conductors who have different resistances, then the conductor with a greater resistance will produce more heat as compared to the conductor with a less resistance. Similarly, if different currents are passing through two conductors of same resistance, then the greater current will produce greater heat. That means the conductor which is having more current passing through it, it will generate more heat than the resistor in which less current is passing. So the heat produced in any conductor is dependent on two things: the current passing through it and its resistance. Now, a copper wire which has a very low resistance will generate less heat, but a high resistance wire, nichrome wire, which is used for heating elements of electric irons and geysers, it is having a high resistance, so it generates a high amount of heat. Why is it so? Because it offers more resistance, more opposition to the current, and this opposition, or we can say this electrical friction, produces heat. Electric heater, room heater, iron, electric kettle, electric geyser, all these devices are based on the heating effect of current. Even the incandescent bulb and the electric fuse, these are also based on heating effect of current. Heat generated is an energy, heat is a form of energy, and so is work. So we can say that electrical work done or heat generated in a circuit, we take it in the same sense. The work done by a conductor when it flows through a resistance R with an electric charge Q moves against the potential difference V. The amount of work done is given by W is equal to Q into V. We have read this formula, this relation previously. Now, Ohm's law says that V equals I times R. In place of Q, in place of V, we put this. I is equal to IR, and I is Q by T. We have also studied this. The rate of flow of charge is current. So current is charge divided by time. We put this here. So we say that W is equal to I into T into R into I. That means I square RT. So work done is equal to I square times R times T, where I is the current, R is the resistance, and V is the voltage. Now there are two more relations for calculating the amount of heat. Equals, first is this one, I square RT. It also equals V square T upon R, also equals V into I into T. In the first formula, we don't have potential difference. In the second formula, we don't have current. And in the third formula, we don't have resistance. So if you remember these three, then you can very readily use these relations in solving your numerical problems. We can substitute of heat produced for work done. That means electrical energy getting converted to heat energy, and transfer of energy is also called work done. So we can say that this W is the electrical work done by the current when it flows through a circuit whose resistance is R. Now this concept, the electrical power. Power means the rate of doing work or how quickly the work is done or how slowly the work is done. If the work done is slow, we say that power is less, and if the work done is quick, we say that power is more. So electrical power is the rate at which the electrical energy is transferred or converted to heat energy or consumed by the circuit in a particular time. The power measures how quickly tasks are completed. Electrical power refers to the rate at which the electrical energy is used or depleted in a circuit. That means if this term, the I square RT, is divided by T, we get power. Now again, power is measured in watt. The SI unit of power is watt, and you will be asked to define 1 watt of power. So 1 watt of power is when 1 joule of work is done in 1 second, then the power is 1 watt. Like we had three relations for work, similarly we will be having three relations for heat also, like P equals I square R. When we divide it by T, that T gets cancelled. Also equals V square upon R. T is again cancelled. Also equals V into I. Remember these three. It will be of great help in solving your numericals. Now, the applications of heat produced in a conductor or the heating effect of current. The electrical heating appliances, all the heating appliances, whether it's a room heater or a toaster or a oven, whatever, they are using this effect, the heating effect of electrical current. Electric irons, kettles, toasters, ovens, room heaters, water heaters, all are based on the heating effect of current. Even the light bulb is also based on heating effect of current. Remember that bulb with a filament? It is called the incandescent lamp. In that, the filament, when current is passing through it, it glows. First it becomes red hot, then the temperature further increases due to its high resistance, then it becomes yellow hot, and finally at the highest temperature it becomes white hot and it glows and emits light. Also, the electric fuse, a safety device used to protect our appliances against surprisingly high current. So, to prevent them from damage due to a high current, a sudden high current, a fuse is installed. When the high current passes through the fuse, its temperature increases and the material of the fuse is so chosen that it has a low melting point. So when the temperature increases, it melts and breaks, and when the fuse breaks, the circuit is open or circuit is broken, so the current stops, and this prevents our appliances from getting damaged, or even the internal wiring of the building may get damaged due to high current, and in that also fuses are helpful. Nowadays, in place of fuse, we are using miniature circuit breakers. As the current value gets high, the circuit in the MCB gets tripped and the current is stopped. We can remove the fault and we can reset the MCB and the current starts again. That was all in this unit of electricity for class 10. All the best for your studies. Thank you.